And this part here together is the standard error of DI here. So if you can write one more step, you can say EI. This thing here is just the MSE. You can consider this is a sigma hat squared, but with sub I. That means the model has the ith data point deleted. Okay. So put that here. You basically have sigma without square. You still have sigma hat, right? Sigma hat, but without square is sub I. Then you have square root of 1 minus HII. The reason I write this in this form is because I want you to compare this with the Ri without star. So this is Ri without star. So you have EI divided by square root of 1 minus HII, both. The only difference here is you have sigma hat, you have sigma hat with I. Without the I, you basically get from SSE divided by n minus p minus 1. With the I, you get the SSE with I divided by a different degree of freedom, just minus 1 because you have one less data point. Okay, so highly similar, right? It's just the sigma part, the standard error part is different here. So with this, we can conclude the newly defined Ri with the star actually follows T distribution. What do you think the degree of freedom now? Yes, it will be n minus p minus 2. Normally, we would say n minus p minus 1, but that is with n data point. Right now, you have n minus 1 data point, okay? One last data point, that's why you minus 2 now. All right. So now we can conclude it's a T distribution because regarding the definition for T, we already satisfied the first two previously, right? The only one we don't satisfy is the independence. The top and bottoms must be independent. Right now you have EI, you have sigma I. This sigma with sub I, with parentheses here, that basically means it's computed from model that didn't use ith data point. This is ith data point. This one did not use ith data point, so it's independent. EI and sigma hat with I are independent. Okay, because of a newly added this this requirement is satisfied, we are able to conclude this T. Once we know it's a T, the remaining part becomes easy, right? You can use a T test. Use a T test to perform. Basically, if its absolute value is greater than alpha over 2 with this degree freedom, you can consider it's outlier. All right. So this one, Ri and Ri star. Ri is considered internally standardized residue. Ri star would be externally standardized residue. The difference can be seen from here, from this picture. The reason we call that externally standardized is because in order to detect if this data point is outlier, I'm not using this data point to fit the model. I'm only using the remaining part. That's why it's external. But in the first Ri defined, we are actually using all the data points here. All right. Any questions so far? So what is purpose to discuss the residue so far? We talk about the residue just to detect outliers. So here, we talk about residue EI and DI. residue, we talk about the EI and the DI. We also talk about the standard version of that, RI and RI star, right? Know the relationship between each other. RI is derived from EI, RI star is derived from DI. EI is just a straightforward residue, but the DI is a deleted residue. That's why it's called, it started with a D. So this one is called internally standardized, this one is externally standardized. But what is the purpose? Purpose is in order to use them to detect outliers, okay? Use that to detect outliers. All right. So now we have a T distribution. You can simply use that to detect outliers. Do you need me to even write out if the Ti star absolute value greater than TR over 2 and minus P minus 2, consider it is outlier. Okay? We didn't formally write down what is null, what is the alternative. Basically, the null says everything is satisfied. The alternate basically thinks something is violated. But here, the outlier is the only data point that didn't satisfy all of that. Okay, can you use this to detect multiple outliers? That's a very good question. If you only have one outlier, you are using taking one out at a time. You are able to detect that. But if it's a cluster, if it's a cluster of outliers, let's see in here. In here, you not only have one, but also have a cluster of others. Okay. In this case, if you take out one, you still have others. Let's say the number of data points here and here still dramatically different. You may have 100 here. Here you may have like up to 5. If you take out one at a time, this other remaining outlier will still drag this line down toward itself, toward themselves. They still not be able to detect. Okay, so know the limitation of the new method. The new metric here by using RI star is good for one outlier, but for multiple outlier and also clustered. But for the situation we just described, you may still not be able to detect, okay? If you have any question? So if you don't have any question, next we are talking about, okay, how do you visually inspect to detect outlier? This is coming from section 7. Use the residue plot. What if the cluster outlier has greater density than the original cluster? In that case, you would call the original outlier, right? Outlier or not has something to do with how many data points. Let's say you have original data point 5, you have 100 points you consider outlier, but the outlier are all clustered together. You may consider the 5 original point as outlier. Who is the majority? Who is the small percentage? Right now flipped. All right, so next we talk about using visual inspection to detect what is wrong. So still we have the 4 assumptions lying. So we are going to use the residue EI versus the fitted data YI hat. So this is called residue versus fit. You can also use EI versus each of Xij written in this form because I consider X is the ith row means the ith data point. The JS column means the JS predictor. Okay. So basically use what EI versus each of the dimension, each of the predictor variable. This is called residue versus the predictor. In case for simple linear regression, you will only have one predictor. If it's multiple linear regression, this j equal to 1 to p, you can plot EI versus each of the predictor to visually inspect if something is wrong. These two should look very similar. They either are identical or mirror case. If it's identical, that basically means you have a positive coefficient. If it's a mirror image, it's like a left side, right side flip. That basically you have a negative slope for the predictor. I will first show you what it looks normal, what it looks everything is right, and then you will have some idea what if something is wrong. So this is a set of slides I posted this morning. You can look at from your own screen if you have. All right, so what looks like a normal plot? So first of all, this is an example with the responsible variable y is the muscle strength. The predictor variable x is your lifetime consumption of alcohol. It's not need to say that it is negative impact, right? So the more alcohol you drink, the more muscle loss you will have. So your muscle strength will decrease as you drink more alcohol. So this is a fitted data. This is fitted line, regression line here. Y hat equal to 26. This is intercept minus 0.2950x. The slope is negative. This is called the regression plot. When you show y hat versus x, it's called the regression plot. So what is the residual versus the phase plot? So the y-axis here is the EI residual. The x-axis here is the fitted value, is y hat. So this is the EI versus y hat. If you plot out all the i's, you will see here what it looks like. Well, it's random. First of all, if you look at the center of this, it's basically centered around the horizontal line. There's no trend of upward or downwards. It looks very random here. Okay, this is a what if everything is right, well behaved EI versus y hat. So if you plot EI versus x, this is residual versus predictor. If you look at this two, if I make it smaller, you can see two on the same screen. They look very similar, right? They look very similar, and you don't see any problem here, except that this appear at the right. This appear on the left side of one plot. Now go to the right side of the other plot. You see the 3 dot, 2 dot here, and the 3 dot, 2 dot here. That is because you have negative slope. If you have positive slope, they will look very similar. It's like identical. Right now, it's like a mirror image of each other. Right? So this is a normal behavior. Well-behaved plot. So what if something is wrong? Now, here is another example. This one is talking about blood pressure versus a bunch of other factors. For example, age, weight, and duration of some hard activity. I didn't write down the full description. Basically, coming from the physical exam data, your blood pressure intercept here, the age of the person, weight of the person. This is the duration of some cardiac activity. You look at the regression plot. Regression plot also some trend, right? This is BP versus age, blood pressure versus age, blood pressure versus weight, blood pressure versus duration. You won't be able to directly see what is problem, right? You won't be able to immediately conclude something is wrong. But if you plot the residual plot, this is residual versus one of the predictor. So basically, you use the age, only one factor in your model. The model only have age. Then you plot the residual versus another factor you didn't use in the model. This is weight. Then you see a trend. You don't see that randomly distributed around the horizontal line. You see a trend. So residue coming with a model with age only has a clear linear correlation with weight. That basically means your model should add more factor in that. You should probably consider to add weight into your model, okay? Then we have a new model. The new model has both age and weight in the model. Then we plot the residual versus another unused factor, which is duration. The residual is coming from model with age and weight. Then the residual is plotted against duration. Duration is not used in the model. Then you don't see any trend, right? This is a well-behaved, randomly distributed around the horizontal line. In this case, you should stop. You do not need to add duration into the model. So the whole process is like model selection. You start from a small model with only one predictor. Then you see your residual has a trend with another predictor. So you add that, then you plot against the remaining unused one. Then you find out, okay, there's no trend. It's totally random. So this is the time we should stop. We don't need to add another factor into the model, all right? So this is another plot, another example. This is basically the automobile tire, the depth of the groove versus the mileage. So certainly, the longer you drive, the shallower of your groove, right? So you have a negative relationship. This is a regression plot. From the regression plot, most people probably feel it's okay, right? You just look at the plot on the left, you probably are happy with that. But if you plot the residual versus the fit, this is an EI versus YI on the right, what do you see? They are not randomly distributed around the horizontal line. You see a curve. That's a second order curve. So basically, it indicates between your response and predictor, it's not a linear relationship. Using linear model would be wrong. Certainly, this is like something squared. It's a quadratic curve, okay? So what assumption is violated? That's a L, okay? L line assumption, the L indicated linear. In this case, it's not linear. And also here, you see another plot. Just by looking at the regression plot, you can't conveniently conclude something is wrong. But if you look at the residual versus the fit, EI versus Y hat, what do you see? They don't demonstrate equal variance. You see here, it looks like a megaphone. It's very concentrated on the left side, but it's more spread on the right side. Looks like a megaphone. The megaphone could be like a left side small, right side big. Can also be like a left side big, right side small. But either way, it doesn't demonstrate equal variance because the variance on the right side is a lot larger. Okay, so we have seen the example that is well behaved, that scattered randomly around the horizontal line. It's like horizontal band. But the non-well-behaved plot either have a nonlinear trend, just like the quadratic curve, and also this one that has a megaphone plot. So this is basically violation of E. This is a violation of L. Okay. And then we talk about the outlier. If you look at the regression line here, looks like this one dragged a little bit the regression line toward itself, but not too much because the location here, the x value of this point is still within the range. But if you look at the residual versus the fit, look at which one has larger residual. This one certainly has a much bigger residual than the rest. You'll see here, Ri either greater than 3 or less than -3. That's the first internally standardized residual here. You can easily detect this is outlier. Okay, that's all we talked about so far. We haven't talked about the order yet. That is different topic here. So basically, as a summary here, so basically, a well-behaved plot, EI versus the fits Y hat. Y hat or one of the predictor, you should have a line that is EI equal to 0, correspond to your regression line. You have data points randomly distributed on both sides and appear as a horizontal band. That is well-behaved. If something is wrong, let's say you have regression line that shows this is your EI equal to 0 line, but it shows like this. Okay, still EI versus the fit Y hat. This is basically the violation of L. Well, not the linear relationship is violated. But if you see a plot like this, still you have the EI equal to 0 line horizontal. This is a Y hat, but it shows like some small variance here, but very large variance here, like a megaphone. Okay, this is a megaphone. This is validation on the E equal variance. Okay, so this well-behaved one has L and E both satisfied. All right, so I'd like to stop here. Did I miss any question? With enough data points, should we be able to see that the normal disk of E? What is a distribution? A distribution of E, we talked about that, right? It should be normal. Remember, we gave you the distribution E. Distribution E, we derived that. Okay. More points clustered close to the horizontal line. You mean for this plot? Or for what plot? For this plot, more points clustered close to the horizontal line. As long as it looks random enough, it's okay. So basically that means some data has smaller EI, some has larger EI. But as long as overall it looks random enough, that's okay. But if you see like basically you see a trend, something like that. This is like not just one point. So basically, if you have everything, remember in one of the residual plot, we have something like more point have smaller EI, but then all of a sudden you have one point who have larger EI. This is outlier. Okay. Is this what you're talking about? If it's just one point here, sometimes maybe two, having very large EI, others have smaller, this is outlier. But if you have a trend like this, like the previous one, it's not just one point, it has a trend. Smaller EI, larger there. This is a problem with equal variance. The assumption about equal variance do not satisfy. Okay. All right. EI and epsilon has the same distribution. Okay. The answer is no. EI and epsilon I are two different things, okay? Don't assume they are the same. EI depends on your model. Different model will give you different EI, but epsilon I does not. Epsilon I come with the data. So people always have difficulty to distinguish EI and epsilon I. So I want to emphasize that again and again, residue is not the same as epsilon in your model. So the distribution of EI we just derived in this class. Every data point can have a different variance, even though the E assumption is satisfied. Epsilon I, all epsilon I can have the equal variance, sigma squared, but each EI still have different variance. You look at the distribution formula right here. Even though nothing is validated, each of the EI can still have different variance because there's 1 minus HII that depend on I. All right, okay, you can get off now.
Thank you, Prof.
Yeah, okay, bye-bye.